Welcome to this explainer. Today, we're taking a truly fascinating journey. We're going to start by looking at the absolute tiniest invisible particles known to science, and we're going to trace their rules all the way up to the grand macro-level architecture of the universe. It's a story of how the very small totally dictates everything about the very large.
So let's dive right into this master blueprint. What we have is a direct connection between the nucleus and its orbiting electrons right out to the structured blocks of the elements themselves. What we're going to see is that the invisible subatomic world of quantum mechanics entirely dictates this macro structure. The periodic table isn't just some random list, it's a direct physical map of quantum math.
Here's a roadmap for the explainer. We'll hit the subatomic foundation, check out the quantum revolution, map the quantum address system, learn the rules of assembly, explore macro-organization, and finally arrive at the modern blueprint.
Part 1. The subatomic foundation. We build our foundation with the three fundamental particles that make up, well, every atom in existence. You've got the negatively charged electrons discovered by J.J. Thomson. Then, your positively charged protons residing deep down in the nucleus, discovered by Goldstein. And finally, the neutral neutrons, discovered by Chadwick, which pack in the atomic mass. These are essentially the three fundamental pieces of Lego, from which absolutely everything else is constructed.
Part 2. The Quantum Revolution. Here is where we see a massive scientific shift. For a really long time, we thought of energy purely as a continuous wave, something proposed way back by Huygens in the 17th century, where things like diffraction completely make sense. But by the 20th century, Einstein and Planck introduced the particle nature of radiation. Energy doesn't just flow continuously, it actually travels in discrete little packets called photons. This dual nature, acting as both a continuous wave and a discrete particle, is our gateway into quantum mechanics.
And bringing that dual nature into focus leads us to a pretty huge problem for classical physics. The crucial point here is Heisenberg's uncertainty principle. Heisenberg mathematically proved that it is utterly impossible to simultaneously determine both the exact position and momentum of a microscopic particle with high accuracy. Newton's laws just completely fail at this scale. We literally cannot map a microscopic particle's exact path with absolute precision. No way.
Because of these classical flaws, like failing to explain multi-electron atoms or magnetic field splitting, science had to shift entirely away from the idea of electrons orbiting the nucleus in perfect little planetary circles. Instead, we shifted to wave mechanics. We had to embrace probability density. That concept of a glowing probability cloud isn't a physical object. It represents a 95% probability of finding an electron in a specific spatial region. It's not where the electron is, it's where it might be.
Part 3. The Quantum Address System.
So, if the exact path of an electron is completely unknowable, how on earth do we map an atom? Well, quantum mechanics gave us a brilliant solution. Think of these four quantum numbers like trying to find a person. It's basically a cosmic address system. The principal number n gives us the shell, kind of like the state. The azimuthal number, L, gives us the subshell, like the city. The magnetic number, m, gives us the specific orbital orientation, like the street. And finally, the spin, s, tells us the exact axial motion, clockwise or anti-clockwise, and that's the house. With these four numbers, we can uniquely identify the state of any electron.
And these streets and houses actually take on distinct 3D geometries in space. The subshells aren't just abstract math. The s orbital is a simple non-directional sphere. But as we move up, it gets a lot more complex. The p orbital looks like a dumbbell, the d orbital is like a double dumbbell, all the way up to the highly complex fundamental f orbitals. There are also structural nodes. These are literal dead zones where the probability of finding an electron is exactly 0.
Part 4. Rules of Assembly.
The universe isn't just random. There are three incredibly strict constraints that govern how electrons actually fill these probability spaces around a nucleus. The Aufbau principle, Pauli's exclusion principle, and Hund's rule. Let's break these down.
First up is the Aufbau principle. The easiest way to understand this is simply to remember that electrons are inherently lazy. They will always climb the energy ladder to occupy the lowest energy orbitals first before moving up. We calculate this using the Bohr-Bury rule, which looks at the n plus L values. Because of this math, a 4s orbital actually has lower energy than a 3d orbital, which is exactly why 4s always fills up first.
Once they find their orbital, the next two rules kick in. Pauli's exclusion principle states that no two electrons can have the same four quantum numbers. In practice, this means a maximum of 2 electrons per orbital, and they absolutely must have opposite spins, one up, one down. Then, Hund's rule tells us that electrons prefer to be alone. In degenerated orbitals, like a 2p, they'll fill up empty spaces singly first, with parallel spins, before they finally agree to pair up. These specific constraints are what ensure every atom remains perfectly balanced.
Part 5. Quest for Macro-Organization.
So, we've completely mapped the micro level. Let's zoom all the way out. Long before we knew anything about quantum addresses, how did scientists historically try to categorize the massive variety of elements they were discovering? The evolution of our macro-organization is a super fascinating timeline of trial and error. Back in the 1800s, Dobereiner noticed patterns of 3, which he called triads. By the mid-1800s, Newlands tried to map elements like musical octaves, but, well, that only worked up to calcium. Then Dmitry Mendeleev comes along. He brilliantly arranged 63 elements by atomic mass into a grid, literally leaving blank spaces for elements he predicted would be discovered later. He really is the father of the periodic table.
But Mendeleev's grid had a slight flaw. He organized everything by atomic mass. A massive paradigm shift occurred in the modern era when Henry Moseley came along. We finally realized that atomic mass wasn't the ultimate key to the universe's blueprint. Atomic number was.
Moseley conducted these incredible X-ray frequency experiments and plotted out the data. He definitively proved a perfectly linear relationship between the square root of X-ray frequency and the atomic number. This mathematically proved that atomic number, the exact number of protons in the nucleus, is the fundamental physical property we absolutely have to use to organize the elements.
Part 6. The Modern Blueprint.
Let's see how these domains build our modern framework. Remember those quantum subshell shapes from earlier? The spherical S, the dumbbell P, the complex D and F? Notice how they perfectly match the 4 massive structural domains of the periodic table. The alkali metals form the S block. The halogens and inert gases form the P block. The transition metals, the great catalysts of our world, are the D block. And placed separately down at the bottom, the radioactive inner transition elements make up the F block. The microscopic address directly dictates the macroscopic zip code.
And because it's built on perfect quantum logic, the entire table is alive with predictable, sweeping trends. As you move horizontally across a period, the effective nuclear charge, the literal pull of the nucleus increases, shrinking the atomic radius and making it much harder to remove electrons. But as you move vertically down a group, you're adding entirely new outermost orbits. Those inner electrons act as a shield, pushing the outer layers away, increasing the radius, and vastly changing the metallic character of the elements. It's a perfectly balanced mathematical machine.
We've traveled from the mysterious, unpredictable haze of an electron's probability cloud straight to the rigid, flawlessly predictable columns of the modern periodic table. Knowing what you know now about Aufbau, Pauli, and Heisenberg, how does it change your perspective to realize that the solid, tangible objects you touch every single day are entirely constructed by these invisible, strictly mathematical quantum rules? The blueprint of matter isn't magic, it's magnificent structural logic. Thanks for joining me on this explainer, and keep questioning the world around you.